This is Unit 3, Energy, Lesson 4, Heat Capacity. Let's start with the first problem. An empty copper pot is sitting on a burner. The burner has a mass of 1.2 kilograms and is at a temperature of 130 degrees Celsius. If the pot cools to a room temperature of 21 degrees Celsius, how much thermal energy does it release to the surroundings? So in order to calculate this thermal energy, this change in thermal energy, we're going to use Q equals mc delta T, where Q is heat, and heat is our transfer of energy. Our mass is 1.2 kilograms, times by the specific heat capacity for copper, which is given to you on the front of your handout, times by the change in temperature. It's very important that you have it as the change in temperature, okay, because heat is a transfer of energy. So it's final minus initial. Our final temperature being 21 degrees minus our initial temperature of 130 degrees. This is going to give us a negative number because our copper pot has lost energy to the surroundings, but the surroundings would have gained that energy. So the surroundings would have gained a positive value of 5.0 times 10 to the 4 joules. Moving on to question 2. A 60 gram sample of metal is heated to 100 degrees Celsius before being placed in 200 milliliters of water with an initial temperature of 10 degrees Celsius. The metal-water combination reaches a final temperature of 15.6 degrees Celsius. Determine the identity of the metal. So to determine the identity of the metal, we need to know its specific heat capacity. That is a characteristic property and will help us identify the metal. So we're going to use Q1 plus Q2 equals 0. This comes from energy conservation. If we label Q1 to be the heat gained by the water and Q2 to be the heat lost by the metal, whatever the water gained, the metal would have had to lose. So expanding on that, we have M1C1 delta T1 plus M2C2 delta T2, where 1 is our water and 2 is our metal. But we don't know the mass of water. It simply gives us the volume of water. So recalling the equation for density, where density is mass divided by volume, we can rearrange it to solve for the mass of the water, which is density times volume. And the density of water will be 1 kilogram per liter. Then we can multiply that back by our specific heat capacity of water and the change in temperature. Notice that this is going to be a positive value because the water has gained energy. Then, plus our mass of the metal, times by C2, that's our unknown value that we need to solve for, times by the change in temperature for the metal. You can see right there, it's going to give us a negative value because the metal is losing energy. Rearranging our equation, we can solve for the specific heat capacity of the metal, which turns out to be 9.2 times 10 to the 2 joules per kilogram degrees Celsius. And if you look at the front of your handout, you'll see that is aluminum. Last question, number 3. The specific heat capacity of ethylene glycol is 2,200 joules per kilogram degrees Celsius. Determine the final temperature when 1.73 kilograms of ethylene glycol at 25.4 degrees Celsius are mixed with 2.47 kilograms of ethylene glycol at 89.2 degrees Celsius. So in this case, we're going to do the same thing. Q1 plus Q2 equals 0. But when we expand that to mc delta T, because we're mixing two identical substances together, the specific heat capacity can cancel, and we can simplify the equation a bit. As we sub in our values, remember that delta T is T final minus T initial. Now, each substance has a different initial temperature, but the final temperature is the same. So what we can do is we can expand, collect like terms, meaning we collect our final temperature, and then solve, which gives us a final temperature of 62.9 degrees Celsius.